speakers. We have 3 speakers today. The more the merrier, as we say. Our session is about diving deep into algorithm, decision trees, and random forest. Before the session begins, I will just want to give you a heads up what is our ML series. Next session will be diving deep into algorithms, unsupervised learning, and evaluation metrics, accuracy, precision, recall, F1 score, and ROC. It will be on the same time on 16th March. So don't forget to join. Or to your speakers.
Okay, thank you so much, Hema, for that wonderful introduction. All right, so I'll just share my screen. Yeah, is my screen visible?
Yes.
All right, great. So hello everyone and welcome to today's session. So today we'll be talking a lot about decision trees and random forests. So let's jump right in. So first we'll have a small recap of what we did last time. So last time we learned all about SVM and naive Bayes. So we learned that both SVM and naive Bayes are supervised learning algorithms. Naive Bayes is mainly used for classification and SVM can be used for both regression as well as classification. Now naive Bayes assumes that every feature is independent of one another and it follows something known as the Bayes formula. While SVM essentially helps you plot a decision boundary between given classes. So that was about SVM and naive Bayes. So today we'll be talking about decision trees, the use cases of decision trees, random forest, its use cases, as well as a comparison between decision trees as well as random forests. All right, so let's get started. Now, picture this scenario. So let's assume that there are a few girls who are walking back home from school and they stop and they pass by their favorite local cafe and they really want to go there. But you know, as schoolgirls, you don't usually impulsively just go to cafes. You always sit back and think a little bit of some features before you go there. So you can assume that one of the features they think about is, do they have money? Do they have money enough to go and buy something from that cafe? Could you all maybe type out in the chat, what other things could they think of? Could they decide upon before they go into this cafe and, you know, maybe enjoy some food over there? Any other factors or features that they would keep in mind before they, you know, enter this cafe? What time of the day? Will the parents catch us? Yes. Ambience, nice. Time, yeah. Do their parents allow it? Yes. Post-school activities, amazing. These are all amazing answers. Is it a popular place? Yeah. Is it a well-known place? That's correct. Energy. Does their phone have enough battery? That I really like that answer. Food choices, menu, what they should wear. Yep, money, free Wi-Fi. Lots and lots of amazing answers. So these are like features that we almost all the time think of when we like maybe are going to a new place. So I've just listed out a few here. Maybe money, and if they have some work or assignment or exam due tomorrow or not. And very importantly for schoolgirls, especially if their parents will allow them or not. So based on these decisions, they will choose if they go to the cafe or go to their respective homes. So let's assume that, okay, so they do want to go to the cafe really badly. And they do realize that they have money. So what do they think of next? They're like, okay, now we have money. What are the other factors that could possibly stop us from going? So then they're like, okay, let's reassess. Do we have any work for tomorrow? Maybe they don't. They got lucky. And then the final call to their parents. Will their parents allow them? And surprisingly, their parents allow them too. So they all go to the cafe. So you can see that there are a few simple tasks here. And a simple yes or no to these tasks led to a particular outcome. So that is essentially what a decision tree is. It's in machine learning as well. You have sequential decisions based on certain features that help you with the outcome. So these features that help you with the outcome, there are certain sequential decisions that you take with them to land at that outcome. So a decision tree is basically a supervised machine learning model that helps you either perform classification or regression. So what exactly do you do here? Here, you have a series of sequential decisions that you make for you to reach the specific result. So in the previous example as well, we saw that first we discussed if they have money or not. Then they went on to if they have work tomorrow or not. Then they went on to if their parents will allow them or not. And based on whether it was yes or no to all of these decisions, they landed at the outcome of yes, because all of these worked out well for them. So they landed at the outcome of yes, they will be going to a cafe. So this can be modeled in many machine learning applications as well. Let's take, for example, you want to build a machine learning model that can predict if a person has, let's say, heart disease or not, or heart attack or not. So some features you'll take into account is chest pain, arm pain, low blood circulation. And for each of these features, so these features or attributes are what help you define or decide on the outcome. So for each of these features, what will we do? We will see if there is chest pain, then there's a probability that it could be a heart attack. Is there low circulation? Probability that it could be a heart attack. If there's arm pain, there's a probability that it could be a heart attack. So for each of these features, we see and decide how it can affect the outcome. Based on that, we take a yes or a no decision, and that will help us predict the final outcome, whether the person has heart attack or not. So this can be used for regression as well as classification. So for classification, the final outcome will be a class. So in the example that I just mentioned, if it's like if the person has a heart attack or not, has a heart attack is one class, does not have a heart attack is another class. It can be used for regression as well. Maybe your final answer is not simply just yes or no. It could be like some sort of value, like a numeric value. So in that case, the decision tree can help you model regression. So yeah, the features and attributes of a decision tree, it basically varies depending upon the complexity of the data that you have. Now, so you can think of this as an example of a decision tree. So this decision tree's main motive is to predict if a given fruit is an apple or not. So whatever fruits that are passed to, maybe it takes into consideration some of its features. Let's say the shape, the color, the taste, and things like that. And based on that, it classifies it as not apple or an apple. All right. So when it comes to decision trees, there are some very important terms that are there with decision trees that we all must know so we can understand the decision trees better. So starting with root of the decision tree. So I'll be using this example to help you understand better. So this is how a normal decision tree looks like. This is the root of the decision tree. So usually here as well, there'll be a question that's asked. Like, so if let's go back to that heart attack example. So like I mentioned, there were 3 cases: low blood circulation, if there's a chest pain, or arm pain. So it could maybe start off with chest pain and then no or yes. So whatever the decision tree starts off with, that is known as the root node. Now, next, there's something known as a decision node or an internal node. Now, these are the sub nodes that we get after splitting the root nodes. So what is that? Now, yes, so we have a root node, and the root node asks a particular question. So these are decision nodes. Based on the answer of what was asked in the root node, whatever is split, these are known as the decision nodes or the internal nodes. Now, how can you differentiate between a root node and a decision node? So in a root node, there is always only arrows that are coming out of the root node. There are no arrows to the root node. Root node is a starting point. For a decision node, there could be like arrows that are coming to the decision node as well as moving out of it. So where basically this was influenced by the previous decision, and based on what your answer for this, it could go either this side or that side. Then we have something known as a leaf node or the terminal node. And this leaf node is basically at the end of the tree. So this is your answer. So in our example, the leaf node would be has a heart attack or does not have a heart attack. So now a leaf node, how can you differentiate it from a root node or a decision node? Well, it only has an arrow coming to it. It has no arrows that are going out of it. So this is where it terminates. That's why it's known as a leaf node or a terminal node. Now, what is splitting? So splitting is basically the act of dividing a root node into some sub-nodes based on certain conditions. So let's say based on a heart attack example, this was good circulation. So if it's no, then it splits here. If it's yes, then it splits here. So that is known as splitting. You have a condition based on what your outcome is for that particular condition. You can go either in the no direction or in the yes direction. Then we have a branch. So a branch is basically a subtree that is formed by splitting the main tree. So what is splitting? Splitting is you have a node, and based on the decision taken by the node, either yes or no, it goes to other subnodes. Now a subtree that's formed. So this is a subtree that was formed by taking this split. This split gave you this subtree. So that is known as a branch. So just to quickly reiterate these important terms, we have a root node. Sorry, just a minute. Yeah, hello, sorry. Sorry about that. Can you hear me? Okay, all right. So yeah, like I was mentioning, so we can just revise these concepts again. So a root node is the node that is present at the start of the decision tree. And then you have decision nodes. These are internal nodes where arrows come into as well as merge out of that decision node. Then we have a terminal node or the node that's present at the complete end. So this node is what gives you the answer for that particular regression or classification problem. Then we have something known as split. So at whatever node there is, based on the decision it takes, it could go either in one direction or the other direction. So that is known as splitting. And we have a branch. So based on whatever has been split, there is a subtree that is formed. So that subtree is always known as the branch. So these are some popular terminologies that are always associated with decision trees. All right. So far we've understood what a decision tree is. It helps you basically you have sequential decisions, and based on these sequential decisions, you get an outcome. So we've now understood that there is definitely a use case of these decision trees. It could be either classification or regression. Now we've understood where we can use decision trees and what it is. But the next question is, how do we build it? No, we don't build it by simply sowing seeds. So what do we do for this type of decision tree? To build it, as with most things that we build, we always have algorithms. So to build a decision tree, there are different types of algorithms. Some of them are mentioned here, known as CART or classification and regression trees. We have something known as ID3. But the main question is, you have so many different nodes. What feature should come here? What feature should come here? We know that the terminal node will always be the output, but there could be several nodes in between. So what question should come there, or what feature should come there? What is the priority order of these features? So let's go back to the heart attack example. We had low blood circulation, we had chest pain, we had arm pain. So should the root node be arm pain? Should it be chest pain? Should it be low blood circulation? And if the root node is, let's say, low blood circulation, what should this node be? And what should the subsequent nodes be? So how do we get to decide this? Or if I have to sum it up, which question do we ask first? What is the most important feature, and how do we rank these features in order of importance? So this is the basis of building a decision tree. If we know what question we need to answer, if we know which feature is the most important, and the second one and the third one, basically, if we're able to rank our features, then we've basically built a decision tree. Because we already do know our outputs. Whenever we take a problem, this is a supervised machine learning algorithm. So you always have the target associated with it. So we do know what outcome we want. So that is there. The terminal node is there. But what about the root nodes and the decision nodes? So to figure that out, we have something known as the attribute selection measures. So these attribute selection measures will basically tell you which feature is important. Which feature should you rank first? Which feature should be second? Which feature should be third? And gives you their order of priority or order of importance of these features. So this is known as attribute selection measures. So that's what helps you basically list out or rank out your features. There are two types of attribute selection measures. Actually, there are many more than two, but in this session, we'll be talking about two. So one is something known as a Genie impurity, and another is something known as information gain. So Genie impurity is based on a concept called impurity. Information gain is based on a concept called entropy. We'll discuss all of these terms in detail right now. All right. So now let's take this running example so that we understand all the concepts better. So let's take this data set now. We have two features, degree, experience, and we have the target column, placed or not placed. So placed or not placed meaning if the person has got a job or not. So based on their degree as well as their years of experience, has this person got a job or not? This is a data set we have. From this data set, we want to build a decision tree. So what do? Which feature should come on top? Should degree come on top and then experience in years come up? Or should experience come first and then degree? We don't know that. So let's see how we can build that. All right. So this is basically how the decision tree can be built. We can either have degree on top and experience, or experience on top and then degree. So if you can see, when we have degree on top and then we have experience, based on whether it's bachelor's or master's, we can see that based on if it's you have degree and then you have bachelor's and experience is more than 2 years, then you get these as your outcomes. So this was the data set. And from this data set, we basically built that tree. So based on if we get started with degree. So we first get started with degree, and from master's, so we can check that. So let's say you have degree and then you go to bachelor's. So bachelor's and experience greater than 2 years. So okay, that data is probably not here. It's actually a snippet from a much larger data set. So yeah, that's how we try. We look for bachelor's, then experience greater than 2 years, and then we check the outcome. So that's basically what we've done here. So we look for degree, then experience greater than 2 years, and then we check if that person has been placed or not, that has gotten a job or not. Similarly for masters, we check if it's masters, then experience is less than 2 years. We check this. Same way, we check for, now here we've interchanged the features. So we put experience first, and then masters or bachelors. Now for this tree, we have something known as entropy that is high, information gain is low, and Genie impurity is high, while it's the opposite here for this tree. So let's understand that in detail. So first, I'll explain what impurity is. So impurity basically means the homogeneity of a node. So what does that mean? Let's take this example that's present on screen. So let's say you have a basket full of apples. Now you have another bowl here that has a lot of labels containing the word apple. What is your job here? Your job here is to take an apple from the basket and match it to a label in the bowl that has the word apple. So you got to take an apple from this basket, match it to a label here that has the word apple. Now, what is the probability that you will do this correctly? 100% probability, because there are only apples here and there are only apple labels in the bowl. So definitely, no matter what, you will always take an apple from the basket and match it to a label called apple that's present in the bowl. So this means that it's a pure node. So that means that there's only one type of class. There is only apple. So you obviously will take apple and match the apple. So impurity is zero here. There is just simply one type of thing, one type of thing. That one type of fruit here we have is apple. So now let's check this fruit basket. It has a variety of fruits. So now let's say you want to take a banana and match it to another label. So you want to take a banana from here and you want to match it to a label in this bowl that has the word banana. Now you can't do this with 100% probability because this bowl has a lot of other labels like, it has a lot of other labels like apples, kiwi, maybe grapes and things like that. So what is the probability? The probability is definitely not 100%. You could match a banana with grapes and have incorrect matching in that way. So the impurity here is not equal to zero. So that means there is some impurity that's present here. Why? Because you have multiple classes or multiple types of fruits. Here you simply had one type of fruit. You had to take an apple and you had to match it with a label apple in that bowl. And there was only apple in the basket. There was only apple labels in that bowl. So it was very easy for you to match it with 100% probability. But here, for you to take a banana and match it to label banana, it is not always 100%. Sometimes you could go incorrectly. You could, like in this example, match a banana with a grapes. So that's known as impurity. So if we go back here, we see that when it comes to, when we make the decision tree in this manner, that is, we have the degree first. The degree is given the most importance, and then we're giving importance to the experience. Then the final target has 4. That is, we have based on the data set here. So based on the data set, we have either placed, not placed, placed and not placed. So we have both classes of data over here. And here also we have both classes of data. Here it's completely pure. This is what I mean by pure node. That is, we simply have one class of data. Here all the four outcomes are placed. So if you're still confused as to why there are 4 outcomes, it's based from this data set. So from this data set, and this is just a snippet from a larger data set. So from this data set, if you check for degree, bachelor's and experience greater than 2, you'll find one data point that is one outcome that's placed, another outcome that's not placed, another outcome that's placed, another outcome that's not placed. So we're basically trying to model this data set into this decision tree. So when we do it that way, we see that we have this node is impure because it has both classes. This node is also impure because it has 2 classes. But this node is completely pure because it just has one class. Again, this node is also impure because it has 2 classes. So based on this concept only, we have something known as Genie impurity. So Genie impurity helps you find the homogeneity of a node. Now, what is this Genie impurity? It is the likelihood that a randomly selected sample would be incorrectly classified by the node. So using this metric known as Genie impurity, what you're trying to do is you're trying to figure out how wrong will this feature go? How wrong will this feature classify your output label? So like you have here, how wrong will it go? Like, it does not mean that these are wrong, but it means that the purity is not that much. There is a lot of impurity here because there are two different classes. So the main question is how wrong can your feature go in predicting? That is known as Genie impurity. Now this Genie impurity value ranges from 0 to 1. Zero impurity means that they all belong to one class. So like we saw here, it was zero impurity here. So it was all apples, just belongs to one class. That way, this is also going to be zero impurity. They all belong to one class. So when there is zero impurity or lesser impurity, we know that this feature is doing a good job of separating the data. It's doing a good job of classifying the data. While this way, this manner, it's not doing that great of a job, because here you have a lot of impurity and so do you have a lot of impurity here. So that's why we have the Genie impurity value high here, while the Genie impurity value low over here. Low over here because it's doing a good job of separating the data. So you have to basically ultimately you have to divide your data based on the experience and degree into either placed or not placed. And this, when you arrange the tree in this manner, it's doing a better job of splitting the data into placed and not placed than this particular way of arranging things. So that's why whenever we look for which node to split or which feature should we use first, we always calculate the Genie impurity of all those features. Whichever feature has the lowest Genie impurity, we put that as the root node. And then the second lowest, we put that as the middle node. Like that, we always rank the Genie impurities in ascending order, the lowest first. So the feature that's associated with the lowest Genie impurity, that comes on top. And it goes in that manner till the terminal or the leaf node. So yeah, so 0 means that the terminal, so it means that elements belong to one class, and 1 means that if your impurity is 1, that's totally impure, that means that you have many different classes, and that particular feature is not helping you do a good job of classifying your data into those classes. So that's what Genie impurity is all about. So now, like I mentioned, there are two different methods. So we learned about impurity. So impurity is basically how good your feature does, how well your feature basically classifies that data point as one class or the other. So when we looked at this tree does a better job of classifying your data because it has one clear class here and almost another class over here. So the lesser the Genie impurity, the better. You want to aim for purer nodes. You want to basically use that Genie impurity quotient as a metric for you to classify the data. So for you to classify the data, you need to have a clear distinction. So that's why tree is doing a better job than this tree. Now let's look at the last concept, that is entropy. So many of you may have come across this term known as entropy. What is entropy? Entropy is basically randomness in data. It indicates how messy our data can get. So this is high entropy, that is like very, very messy. And this is low impurity, that is relatively cleaner. So high entropy is very messy. So if I go back to this example, this has low entropy. There is no much randomness in our data here, but this has a high entropy. There are many, many different classes in this because you have pineapples, bananas, kiwis, apples, so many different fruits. But this has just simply one kind of fruit, that is apple. So this is low entropy, while this is high entropy. So that's about entropy. Now, entropy is going to be used in another metric known as information gain. And this information gain is a metric similar to Genie impurity. And this also can be used to determine which feature should get the highest priority. So what is information gain? Information gain, just as the name suggests, is the measure of how much information a feature can give us about the final output. So using information gain, we're basically trying to figure out how much information can we gather about the final output from this particular feature. The more information you can gather, the higher the ranking will go. So here, it's in evaluation way, it's opposite to Genie impurity. You wanted lower Genie impurity. Lower the Genie impurity, the higher the priority that feature gets. But in information gain, it's higher the information gain, higher the priority that feature gets. Why is that? So again, information gain ranges between 0 and 1. Again, higher the information gain, better the split, and it's inversely proportional to entropy. So I'll explain all this. So let's go back here.
Sneha,
Okay.
can you we have some questions. Can you take up a question?
Yeah, just a second. I'll just quickly finish
Okay, yeah,
explaining
sure.
this. All right. So entropy, right? Now let's come back here. Let's assume that you had like entropy of around 50 over here. Like I know it ranges between 0 and 1, but let's just assume you had entropy of, let's say, 50. And when you come over here, you had an entropy of just 10. So your information gain is the difference between entropy here and entropy here. So 50 minus 10, 40. 40 is your information gain. That is your entropy, information gain. You want your information gain to be as high as possible. Why is that? There's a lot of randomness here, let's assume. But that randomness has been reduced a lot when you use this feature. That's what it means. You do not want a lot of randomness in your data. So when that randomness can be significantly reduced, then you put that node on top. Whichever node can help you reduce the randomness, that's the node you give higher priority to. That is the difference between the first randomness and the second randomness. That is, first entropy and second entropy should be a lot. In that case, you have a higher information gain for that feature, and that feature will be on top. So if you can see here, there is still a lot of randomness here. There are both classes here as well. So your entropy is relatively high here. And entropy is inversely proportional to information gain. Why is that? We're trying to reduce the entropy. Information gain is a mean of basically, one entropy, that's the entropy here, minus the entropy here. We want the largest possible differences between the entropy. That means that the entropy has significantly reduced. So that is why information gain is inversely proportional to entropy. And here the information gain is very low. We're not really learning a lot about the data by putting degree first. Rather, if we put experience first, we see that there may have been a lot of randomness here. But when it has been split in this manner, the entropy is low. It's not as random over here. It's not as random over here. So the entropy is low. And because the entropy is low, you're getting to learn a lot about the data. You're understanding that, okay, if their experience is greater than 2 years and they've done their masters, then all of them have been placed. So you're learning a lot about the data and you're finding definitive ways to basically split the data. So that is why information gain should be high whenever your entropy should be low. You're trying to minimize your entropy and maximize your information gain. That is the difference in the entropy. So that's about Genie impurity and entropy. So Genie impurity is a measure of how impure your node is. How many different classes are there? You want to reduce the impurity as much as you can. You want to have as much as you can. You want to just have a single class, or the ratio of classes should be very little. And that is happening with this arrangement of features. So you have more of placed here, and this is a purer node. And when it comes to entropy, entropy is the randomness in data. So when it comes to entropy, you basically want to reduce the entropy. So when you're trying to reduce the entropy, you want to reduce the randomness and increase the information gain, which is the difference in the entropy from one level to another. So you want to increase the information gain, reduce entropy, and also reduce the Genie impurity. All right, I'll take up some questions. Yeah, Brandy wants to clarify. You said the root node would have the lowest Genie impurity. Yes, the root node will always have the lowest Genie impurity. Root node will have the lowest Genie impurity, and root node should be taken in such a way that it has the highest information gain. I hope that helped you, Brandy. How does Genie impurity differ from a correlation? How does Genie impurity is quite different from correlation. In correlation, you're trying to figure out how much one feature is dependent on the other. When you take like heat maps and Seaborn, if there are three, four features, you're trying to figure out how much one feature is dependent on the other, or how, like, if one feature increases, the other feature also increases. If one feature decreases, the other also decreases. That is positive correlation, or negative as well. So you're trying to, that's positive and negative correlation. So basically, in simple words, you're in Seaborn or heat maps, what you're trying to do is that you're trying to figure out how much one feature depends on the other. But in Genie impurity, it's not like that. What you're trying to do is you're giving a priority order to different features, and based on these two features, how well are you able to categorize a data point? How well are you able to get the outcome? So let's say a person has a degree of bachelor's and has greater than 2 years of experience. So when it comes to this types of, okay, that's data point. So person has bachelor's degree and greater than 2 years of experience. You want to find out if that person will be placed or not, if that person will get a job or not. Does this data set does this decision tree do a good job in categorizing that? It does not, because you don't exactly know whether they will be placed or not placed. But here, if you reverse the order in which you're taking the features, if you first check if that person has more than 2 years of experience, then you check if they have a bachelor's or the master's, then you can clearly see that, okay, here also, if they have more than 2 years of experience and they've done their bachelor's, you can see that mostly they will not be placed. However, if they've more than 2 years of experience and they have done their masters, mostly they will be placed. So this Genie impurity is basically finding the purity of a node. So purity is nowhere related to a heat map or a correlation map. Correlation finds the dependency between two features. Here, you're using both those features to find the outcome. So that's how they are different. I hope that helped you, Heidi. I'll maybe take one more question and I'll type out the answers for the rest in the interest of time. In the second decision tree, would the node with the lowest Genie impurity, i.e. masters, become the root node? No. So basically, okay, these are the features. These are the features you have, and this is the outcome. These features plus this outcome is what you want to use in building the decision tree. Now, you have only two options. Either put this as the root node, this as the decision node, or put this as the root node and this as the decision node. So like this has two options and this also has two options, right? So if you put degree as the root node, it has either bachelor's or master's. If you put experience as the root node, it has either greater than 2 years, it has either yes or no. So when this is the root node in this case, that is degree is the root node. From degree, it can split either as bachelor's or master's. And this was not doing a good job of basically categorizing a new data point because it has a lot of impurity, lot of entropy, and very low information gain. But when it comes to this, when its experience is greater than 2 years, you can see that once you say whether experience greater than 2 years is either yes or no, once based on this node, you're splitting it, and then you're using this degree. Degree is given second priority and experience is given first priority. In that case, you're able to split that data better. So this is why this has lower Genie impurity, lower entropy, and higher information gain. All right, I'll be typing out the rest of the questions immediately. So yeah, I'll just finish with the advantages and disadvantages. So advantages of decision tree is basically that since, it's just one simple tree, it's very easy to understand and interpret. And when it comes to this, most machine learning algorithms have very messy data. So they require a lot of cleaning. But when it comes to decision trees, they don't require that much of cleaning. Now, disadvantage is that it's very prone to overfitting. It's easy for us to, okay, like more of this will be explained in random forest because random forest is a way that will help you remove the overfitting. So why can it be overfit? Because you have all this data and you simply have one decision tree that will give you the output. So that is why it is very prone to overfit. It's very easy that, a decision tree could go into the overfitting mode. And that's why the accuracy is not always very high. And another disadvantage of decision tree is that it's not very good when it comes to regression. Although decision trees can be used with regression, it's better suited for classification than regression. Because even when you're doing regression, what you're doing is based on these features that you have, you're categorizing things. You're categorizing things based on the features. And in the end, you're predicting a label. So here, in the end, you're predicting whether it's placed or not placed. But in the case of regression, you'll print some numerical value. What happens when you do that? You're first categorizing everything, and in the end, you're predicting a numerical value. So when you take that route, what happens is that there could be a loss of information during categorization. So that's what that could happen. You could lose some important information because you're basically categorizing everything. So it's not very good for regression. It's prone to overfitting, but it's very simple and easy to interpret, and lesser data is required, or like lesser cleaning is required when compared to other algorithms. So that's all about decision trees. I understand that maybe impurity and entropy can be a little bit difficult to take in. So please do ask all your questions in the Q&A box, and I don't mind explaining it all over again. So yeah, do ask your questions and I'll be happy to answer them. Over to Shruti, who will be talking about random forest.
Thank you so much, Sneha. Hi, everyone. My name is Shridhar. So I'm a software engineer at a startup called Motork, and I'm based out of USA currently. Uh, so um, so we learned a lot about decision trees, and we saw where it is used. We saw some advantages, some disadvantages, and we also went through some examples. So let's see how decision trees transform into a random forest. So in the example that Sneha started with, we saw that we consider a lot of features and a lot of questions when we decide even for a simple thing like going to a cafe. So we look at what kind of menu that we want, whether our parents will let us go, how much will it cost, and those things, right? And after that, we also need to consider one thing when we do go to a cafe in a group setting. So ideally, if we are going with our friends, what happens is each person might want to go to a different place, right? So they might have their own interests, like let's say if Sneha, I, and Zareen are going to want to go out to have some coffee, Sneha might prioritize some place that is very close to where our college is, and I might try to prioritize the cost of the coffee that we might be getting there, or any bakery that we might be getting there. So how do we decide as a group at the end of the day? How do we decide as to which one we are going in? We share our priorities, we share what we would like to go, our preferences, and then at the end of the day, the place that we end up going is mostly based on the major vote. Like, let's say both Sneha and I choose a place, or Sneha and Zareen chooses a place, but I choose a different one. We are most likely going to go with the one that they chose, right? So this is what random forest is about. So instead of depending on a single tree, and the decision made by a single decision tree, we trained different decision trees on the same sample, but we consider different features in each of these trees with different priorities, and we take the maximal vote, and that will be the final decision from the random forest. Sneha, can you go on to the next slide? Yeah. So let's look at it in terms of in more definitive terms. So basically, a random forest is an algorithm where we combine a large number of the individual decision trees and make it operate as an ensemble. So what is an ensemble? So ensemble algorithms are basically algorithms where we don't use a single machine learning algorithm, but instead use um, multiple many of those. And instead of just depending on one of them, we depend on the predictive accuracy and the predictive power of the multiple algorithms as one. So we will be looking at ensemble more in the future session. So we will limit to the methods just pertaining to random forest in this session. So as I mentioned, we will have each individual tree making a decision, and the final prediction of the random forest will be the max vote of individual trees. So max vote, or the mode, is taken when we use classification, and averaging is taken when we do a regression. Basically, random forest is an algorithm which can be used both for classification and regression tasks, but they are mainly used for regression classification tasks. So here on the right is just like an example. So here we have like nine trees, right, and nine individual decision trees, and here we are trying to predict whether it's a 0 or 1. They can stand for any class. So let's consider this as a binary classification, and we have 6 1 prediction and only 3 zeros. So we go with the final prediction of 1 because that is the max vote. Sneha, on to the next slide. So let's look more into what exactly we do in building the random forest and how we couple the individual decision trees together to form the random forest. So what we do is we take the training data, we take the original data that we have, and we get samples of data with replacements instead of using it as the whole like we did in decision tree. So we generate different samples of set, and we can also have replace data. For example, If we have a data which has 1 to 6 numbers in it, one random sample might have one, three twos, and then two fours in it. So we can have the same data points again. And why do we do this? This is our way of prioritizing and diversifying what each decision tree prioritizes and chooses the final prediction on. So first, we generate these random samples of data with replacement, and this is called row sampling. And we generate a multitude set of this depending on the number of individual decision trees that we want in our random forest algorithm. And this whole step together is called bootstrap. And in the next step, what we do is we train train each random sample as one decision tree and generate the individual prediction from each of these models. And as I mentioned, the final prediction of the random forest is going to be the max vote of the individual models in case of classification, and the average in case of regression. So as you can see on the right side, we have the original data, and you see the color points representing how these different points are taken, right? We have similar sample set. We have 10 as the sample size, but how many times each data point is taken is differing across each of those individual models. So once we do the bootstrapping step, we build a classifier for each of these steps, and then we combine all of these together to make the ensemble classifier, in this case a random forest, and get the prediction out of that. So there are different ensemble methods, and the one that random forest uses is called bagging method, and which is a short form of bootstrap and aggregation, which I just explained. So let's go on to the next slide. Okay, so what are some of the effective, like what are some features or important characteristics of effective random forest that we have? So one thing that is very important and is a good characteristic of effective RF is the diversity. Since we are doing random sampling of data, we end up with a diverse feature like classifier. Like each of the individual decision tree are uncorrelated with each other and are diverse in their own predictions. So as you see on the right side, if we have just a decision tree on its original data, we might be using all features. In this case, let's say we have 4 features, and the decision tree uses all these features to make the prediction. Whereas in random forest, because we use a sample of data for each of the individual trees, in the first tree, we only have feature 2 and 3. And in the second tree, we only have feature 1 and 3. So their prediction and their priorities are diverse and they are uncorrelated. And so this is one of the important features of random forest. So what's the next thing that we get as an advantage from this? We are not affected by curse of dimensionality. So what does curse of dimensionality mean? So when we have data which has a lot of dimensions or a lot of features, we end up with a problem where we are not able to visualize, or we are not able to use all of them because it has very high dimensions than what we are used to picturing in real life. In real life, we are used to 2 dimensions, we are used to 3 dimensions, or even if we consider time as another dimensions, possibly 4. But a lot of data that we have so many features, right? Like as we've seen before, even for predicting something like house value, we might have number of rooms, previous sale value, inflation, number of bathrooms, the square feet, and so on, right? So one main advantage of using random forest is, since we are doing sampling, we don't have to use all of these features in all the individual trees. So we can build different trees on few of the dimensions and combine all of them together to make the final decision. So that is one big advantage. And another thing is, though we have multiple decision trees, we can still parallelize the training and generation of the prediction of the individual decision tree that we have. So if as a project or for a hackathon, let's say women who code data science is working on a random forest classifier, I can build my own decision tree, and so can everyone else participating. And then finally, we just work together to club it and make the final decision. And let's move on to the next one. So another advantage of this is we are also looking at more features, and we are also doing it without having a lot of disadvantages, and we are not overfitting it. So this leads to more accuracy in itself. So these are some of the main features and characteristics of good random forest algorithms or models. Let's go on to the next one. So let's look at one of the examples. So in this case, the problem that we have at hand is finding what fruit it is that we took from the market or a fruit basket. So we give it through different decision trees in the random forest algorithms, and each which are trained on its own sample, because they might not have been all trained on the same set of inputs. For example, the tree one might have been solely trained only on apple, so it has predicted apple, and the uh, second tree might have been tried on a mix of proper set of like sampled fruits. It might be trained on pineapple, apple, mango, banana, everything, and and our nth tree might just be trained on few of the fruits, right? So here we are passing one of the fruit to a random forest, and we are asking it to predict. So what does it do? It passes this particular data to each of the trees, and here in our case we have tree 1 and 2 predicting apple, and tree n predicting class banana. So we might have other trees also predicting different things, and we are taking the majority voting out of these individual trees, which turns out to, which has been apple, and we give this as the final prediction. um, can we go on to the next slide? Yeah. So now we looked at some of the important features and some common examples. So let's also look at on a broader scale, what are the advantages and disadvantages of random forest. So as I mentioned, one definite advantage, it's more accurate. It's more accurate because we are able to look at different features, and we are able to process it better. We are not overfitting, and also because we are getting a diverse opinion and diverse prediction on its own. Like for example, we can just take how voting works, right? We don't decide prime minister just based on a single person vote. We don't do that, right? It depends on all of the elected members vote, so even opponent and the current one. So that's just a single example. So we are using different points, and we are taking decision based on the whole lot. And and the other one that I mentioned is it is not prone to overfitting, because we are not using the whole data set as one, and we are passing samples of data to individual trees, and each of these trees has samples which might have some of the data points in repeated mode. Basically, it what does it signify? Like I mentioned, the replacement row sampling just signifies that one of these decision tree prioritize this feature or this data point over other. Like I said, if I'm choosing a cafe, if I'm trying to choose a cafe, I might just prioritize money, but someone else might not. So in my sample, the cost data point might be there more than one time. So it is not prone to overfitting, and that's definitely one big advantage over having just a decision tree as the algorithm. But what are some disadvantages? So because we have multiple decision trees, though they can be parallelized, it is still going to take a little more time, because we are still computing individual decision trees and making a few more steps to get the uh, data to those individual decision trees, or also get the output from these individual decision trees. And also this means it's going to take more resources, and it might end up making our computation slow, both time wise and memory wise, also space. So another thing is, like I said, though we do take the overall view of the lot based on the random sampling that we do, and based on how the random sample or the individual decision tree predicts, it can become biased to certain features. Like if in a group, if all of us prioritize money over the quality or over the reviews of a cafe, we are just deciding primarily based on money factor, right? So it can become biased to certain features depending on the sample of data that the decision trees take. Yeah, let's go on to the next one. Okay, now let's look at some applications of decision tree and random forest on whole. So one of the main use cases that we have is credit card fraud analysis. So one advantage or disadvantage of credit card is you just need the number, and CVV is also pretty easy. We don't exactly need OTP all the time, right? So and you just need the address in most cases. So a lot of banks use track your purchases and use it to predict whether a fraud has happened from your credit card. So to give a personal example, right? So when I first got my credit card, I got blocked for a day because my bank thought there was a fraudulent activity that happened on my credit card. Why did they think so? They basically looked at few features like general time of purchases that I do, generally what time do I purchase things at, and they looked at the amount of my purchase. Let's say I'm looking at I generally purchase things less than $500. If I suddenly purchased for more, they might mark it as a fraudulent activity, and they might also look at the frequency of my purchases and so on. So they use all these individual features, and like as Sneha mentioned, they might have their own ordering of these based on how much information they gain for each of these features. And they might have built a decision tree, or they might have built a number of decision trees and used it as a random forest. And they are using it for credit card fraud analysis. This is a real life use case that we have, and it's really interesting. And this is one of the main like this is probably something that even you can build with your own data, and this is really interesting to even track your own data, right? So this is one of the places where we use this. So let's look at another thing, another example. This is prediction. So what do we do when we have any symptoms these days? Before even consulting a doctor, we go and search in Google for i'm I have fever, I have cold, what else? I have headache. And then based on these symptoms, Google literally just shows us a few different things that we might be suffering from. So what is it saying? It is just using decision tree and random forest behind. So it is taking your symptoms in, which stand as individual features, and it is trying to order it. And based on this, it is giving you a prediction of whether this could be a disease or and what exactly this could be. Even for COVID-19, we had CDC and every other health organization showing us what are the different symptoms, right? And what it means if you have these, and how much you might be affected. And if you have these symptoms, you are highly affected or highly infested, you should be taking these steps. So how are they doing this? They are taking all the symptoms and as features, and they are running it through decision tree and random forest based on the data that they've collected till now, and they are giving you the prediction whether you're affected, and if so, how badly. So this is one real-time use case that we are currently experiencing as well. Let's move on to the next one. Yeah, so other things, just like credit card fraud analysis, we are also using it for stock market prediction. So let's say we are trying to invest, like every month you invest 20% of your income in stock market. So what do you generally do? So you look at different things that are currently being talked about, maybe new features that are coming up in each of those stocks, and then you also look at how has the market been for this particular stock over some amount of period, right? Let's say 1 month or 1 week. How is it going? If I invest in this, will I actually get an increase? Or I mean, is this a good investment or not? So you check these things, and based on that, you decide and you do that, right? Similarly, even investment bankers use stock market prediction to decide what to be done. There are a lot of use cases of decision tree and random forest in the financial sector. Let's go on to the next one. One other example is price optimization. So if you look at the prices of items in Amazon or even in any grocery store, they differ a bit depending on weekday, weekend, Also, depending on whether it's a holiday. And for example, if we have a Prime Day sale, there are some things like Amazon items that are always on sale, right? But how do they exactly decide that? It's not just based on that particular event. It's also based on how much this is, how many people buy this item, and how much is it useful today. What are the competitors prices like? So they use different features, and they use that to decide the price of a particular item. So that is another example where we can use a decision tree and random forest. And this is also a good example of a regression random forest, right? Here, since the numbers are continuous, like you can use individual decision trees which predict the data, and you basically are averaging it out to get the final value that you're going to fix for this item. Yeah. Let's go on to the next one. Okay, so now we saw about the applications of random forest and decision trees. We saw about decision trees and random forest in depth. Let's look at the difference now in and which one to use where. Okay, on the left we have a single decision tree, and on the right you have a random forest. As you can see, random forest is a bunch of decision trees, but it can have different samples of data of the original data instead of using the original data as whole, like in the decision tree. Let's next move on to the next slide. Okay, so now we have a poll. Ellen, can you please help me with the poll? Yeah, so here you have to I be able to see the poll? Sneha,
Yes,
can
Shruthi,
you?
it will be just live.
Yeah, I think she's released the poll, so
Okay.
I can see.
Okay, yeah, I think I'm missing it. Sorry. So now what we want to do is there are 10 items there, right? So first, let's match few of these statements, 5 of these statements to decision trees. Which of these characteristics do you think pertains to decision trees over random forest? So let's have 2 minutes for this one.
Hey, Shruthi, could you maybe explain the instructions again? I think.
Yeah, sure. So in this poll, the first question is identifying 5 characteristics. So you see 10 options, right? 5 of these relates to decision trees more compared to random forest. So what I would like you to do is choose 5 of these options which you think is more suitable for decision tree algorithm. And the second one is also available. There you have to choose 5 characteristics which are more related to random forest over decision trees. So the first question is choosing characteristics of decision trees, and the second one is for random forest. Let's take a few minutes for this. Okay. Do we have? Okay. Sneha, can you please share the poll results?
Sure.
Okay, so let's look at each of these and let's see which one is better for you. So let's go on to the next slide as well. Okay, so the first option that we had is suitable for smaller data sets. So many people have chosen this for dysentery. So as we saw, if we have more dimensions or a larger data set, it is better for random forest because we are sampling and creating individual dysenteries. So if we have a smaller data set, it is more suitable for a dysentery because you don't have to, it can easily fit. We won't have the curse of dimensionality problem there. So the first one is for the dysentery. Now the second one that we have has almost no overfitting. So we already saw that since dysentery takes a whole data, while a random forest samples and has a diverse classifier, dysentery has overfitting while random forest does not. So the second characteristic is of random forest. Okay, the third one is accuracy is not that high. Again, because of what we discussed, this also is a characteristic of dysentery. Because we have diverse classifiers and more diversity and less overfitting, and we avoid the curse of dimensionality, random forest is more accurate more than the dysentery. Okay. So many decision trees make it difficult to read. I think the characteristic itself shows which one it belongs to. We have the word many decision trees, so it is a characteristics of random forest. So what we're trying to say is, if you want to, if you try and visualize a decision tree, right? It's really pretty, and it's very easy to follow. Even in the examples that Sneha showed, you're able to see what decision we did, what feature we considered first, and depending on the answers, how did we progress and how did we come to our final prediction, right? When we have multiple of these, it might get hard to track, or it's just more time consuming. You can't really spend time trying to look at each of the decision trees, right? If we have a lot of these in a random forest. So this characteristics, where we have a lot of decision trees and random forest, makes it difficult to visualize and also read or just follow through. And more prone to overfitting is, again, it's the same as the second option. It's the opposite of the second option, so it belongs to decision tree. And easier to read and interpret. It's again the opposite of the one that we discussed last time. You can easily visualize, and you can easily see how the progress goes or how the features or the decision is flowing in a decision tree. So for a considerable size of data, I've done decision trees, and you can actually follow through, even, unless it's a very large data set which is not suitable for decision tree. Decision trees are really easy to visualize and are easy to follow through. And the next one is has a high training time. So let's see, we have one decision tree and we have many decision trees, plus a classifier based on maximum vote, or a regression based on average time. So which one has higher time? Random forest. Higher training time and also higher memory utilization and memory and space utilization for random forest. Next one is works well with large data sets. Again, it's a contradictory point of the first one that we had. This because we have different decision trees, random forest works well with large data sets rather than a decision tree. Provides highly accurate results. So this again is a feature of random forest. So let's also take another example for this, right? So one common example that I can give on a daily basis is when we try to choose not exactly a daily basis, but a common analysis. So when we try to decide what course we want to take for our bachelor's or even our master's, and even what role, if we have considered multiple roles for our career, right? What do? We take different features, but we don't exactly decide what we are doing based on a single person's review of that, or just on based on Google review, right? So what we do, we go to, if you're just Googling it out, we look at different people's review. of a particular course and a particular college. And if you're asking people, we ask different people with expertise in that, right? If I'm trying to choose computer science over ECE, I consider different things like future opportunities, pay scale, how much do I have to pay for the course, and whether it after obviously the first priority might be whether I'm actually interested in it. But other than this, we also look at different people and different reviews, and then decide make a final decision based on this overall, right? So uh, random forest basically shows that it is a machine learning model which captures this common decision making process that humans have. So, and I think the last one was just has a lesser training time. So that again is easy to train and fast is easy and fast to train is decision trees. So we've just put it in a table structure, so it's easy to see here. Just to go over again, decision trees are suitable for smaller data sets, and it is more prone to overfitting and less accurate, but it is easy to read and interpret and easy to train. And all the on the random forest side, it works really well with large data sets, and it does not overfit and has a better accuracy because of diverse classifiers which are uncorrelated. But it does have a disadvantage in training time, and it is not easily visualizable. I think we can go on to the next one. I think that's all we had. Thank you so much for staying throughout the session. Please ask if you have any Q and any questions in the Q&A box. Over to Sneha.
Hey, yeah, so there are some questions. Maybe you could like start answering those as well in the Q&A box.
Sure. Okay, so small data sets can refer to a few different things, right? Yeah. The question is, when the poll mentions small data sets, are we referring to a small number of rows or small number of columns? As a result, how does one deduce whether DT or RF is better for small data sets? So one main thing is the number of columns or the features that we are using, right? And small rows also is a big factor, but the number of features, if we have lesser feature, it is more suitable for decision tree rather than a random forest. In case we have like 10 features, we can use a different decision trees and use it in random forest. So small data sets does mean both of them, but in this scenario we should mainly consider the number of columns or features. So for the second one, also if a DT is prone to overfitting, wouldn't its accuracy be super high? Okay, in a misleading manner. So yeah, so what happens in overfitting? In overfitting, we have a deceiving characteristic that it is high. Its accuracy is high, right? Because it will just be high in the training data. When you are actually testing it somewhere else, its accuracy, because it's overfit to the training data, will be low or will not be as good as a diverse classifier. Okay, and can you explain decision tree why prone to overfitting random forest? So the main reason why decision tree is prone to overfitting is because of how we are sampling the data, and also the diversity and correlation, right? So in decision tree, we take the whole data and we compute feature importance, like information gain at each level, using the whole data set as one, and then we get the output from one. Whereas in random forest, what we do is we take samples of data, and we also do replacement. For example, like I said, if we have a data set which has 6 numbers, 1 to 6, the first tree might just have 1, 2, and 4 in the sample. The second one might have just 1 to 5 in the sample, and so on. So we are trying to show a world where different people, different classifiers or different decision makers are choosing based on different features. They don't have to necessarily choose based on all 6 data points, right? That is one way of introducing or avoiding overfitting. In the decision tree, we are using all the 6 numbers together, whereas in random forest, we are classifying and showing a more real life analysis where some people are deciding based on only subset of the features, and different people choose different subsets. And maybe I'm using all the 6 numbers, whereas Sneha is using 3 numbers and Zareen is using three other numbers. So it is a way of making sure that even if we get only a subset of data in our test, or a case where we have more priority of a subset of data, it still works well and it still predicts with a decent accuracy. And what do you consider a large data set is again related to the first one. It can have a large one of the main things, because we are choosing decision tree and random forest based on the number of features, right? One of the main things is the number of features. So if it has a large number of features, we can consider it a large data set. And another thing, we also care about the rows, but it's more about the number of features and the dimensions. I hope that answers. Anything else? Did anyone else have any other questions? Sneha, is Mansi available for the code overview?
I think we'll take a 2-minute break right now.
Sure. Thank you. Sneha, can you take over then?
Yeah, sure. I'll
Thank
just
you.
share my screen for the time now.
Thank you so much. Thank you so much for staying throughout this.
All right, over to Mansi.
Is my screen visible?
Yeah, it is.
Hi everyone, my name is Mansi and I am from India. Currently, I'm working as a data scientist at an Indian startup called Rupeek, and I'll be taking you through the coding session for this webinar. And I hope you guys can't see that Zoom control bar. That's not blocking the screen, I hope.
No, we can't see that. Yeah.
Okay. So I'm sure this Google link has been shared with everyone in the chat box. and in the Slack channel as well. So go to the session 4 folder and you'll find the decision tree and random forest example notebook, and right click and open it with the Google Collaboratory. So also make a copy, save a copy in Drive. I'll not do that because I have this current copy. So when you make a copy, you'll be able to edit your particular notebook as well. So just do that, and I'm just giving you 10 seconds to do that. So open your copy so that you can edit as we go along. Hope everyone is has done that. Just a few people can just show me in the chat box that they've made a copy. Okay. Okay. Let's go. So we will be focusing on the IRIS dataset. That is an open source dataset, a very simple dataset. And you must have worked on it in the previous session as well. So we'll be using the same dataset. Just a recap, you can run the cells using Shift and Enter in Mac, and I'm sure Control and Enter in Windows. Otherwise, you can just play this and you can run the cell using the play button as well. So first we will import the libraries. You must, for regular attendees who are attending for the 4th time, these are all you must be familiar with these libraries. For others, I'll just go through it quickly. Pandas is the data manipulation or data wrangling library. As means this is an alias. This is a nickname for this particular library that we'll be using in our notebook. Seaborn is for data visualization. Sklearn, we'll be importing the IRIS dataset from this package of this library. For ML models, we'll be using decision tree classifier and random forest classifier of the Sklearn module. For accuracy score metric, we'll be using accuracy score. And for train and test split, we'll be using train and test split from model selection. And this is just to suppress the warnings. We'll just import warnings and ignore all the warnings. So warnings are different from error, and we can ignore those warnings. So let's run. All right. Might take a few seconds because the sklearn libraries are a bit heavy. Host and panelists, you require, please just pause me or interrupt me between the session if someone has a doubt. We don't want the coding session to go along with people having doubt. All right. So please just post your question in the chat, like Q&A box as soon as you have a question, and the host will ask me so that you don't have to carry along with the doubt in your head. So the libraries have been imported, and now we'll go to the data cleaning and visualizing the data. Let's see. So this is just importing the data from the shared URL that has been given, and we'll be reading the data using this URL. This is just a manipulation technique. So URL contains the URL, and then we are splitting the URL at the second last slash. That's it. And pd.read CSV reads the data frame, the CSV files. And we are visualizing the head. Head gives the first 5 rows of the data set. So we'll run this, and so we can see 1, 2, 3, 4, 5 features in our particular data set. That is the sepal length, width in centimeters, petal length in centimeters, and petal width in centimeters, and finally the species, Iris setosa. Here we can see only setosa. Here we can see okay. So if you want to see the last 5 elements of the data set, you say type data df.tail. One more thing, if you just enter 10, that is an optional parameter, you can get the last 10 of the tail. And similarly, for head also, if you want to see the first 10 or maybe 7, you can add an additional parameter. So you'll see this first 7 or the last 10 rows of this particular data set. Okay. We will drop the ID column. ID column is just for a qualitative aspect of the data set. Like this particular row has an ID 141. So this might be the 141st flower or something. This does not add any value to the machine learning model. From machine learning perspective, this is just a numeric serial number. So we don't need that. So we'll use drop. And inside the drop, we'll take a list of columns called, so column parameter will take a list, and that list has only one ID, one column to drop. You can add more columns to this particular list if you want to drop more than one. So we'll just drop this, and just a small snippet of the data set, so you know that it has been dropped. So we don't have ID anymore, and the shape changes to 5 features. DF info will give us like a small compact information of a data set that we have 5 columns. Non-null count, we 150 non-null, that means we don't have any NA or null values in our data set. And data type is the particular column type. So these are all float 64, that means numeric, but with the decimal points. So that is float 64. And this is an object type, categorical variable. Describe will give us some basic statistical descriptions of the data set. So you will see that we have 5 columns, but we have only 4 in describe. That's because the last one is categorical and we cannot calculate the mean, standard deviation, etc. of categorical features. So this will give you the count, mean, standard deviation, minimum, maximum, and the quantiles of the data set. Shape will give you the shape of the data set, that is 150 rows and 5 columns. Is null will give you, okay, let's see what removing the sum gives us. So is null will present a Boolean. Boolean means 0 or 1, true or false in programming language. This will give an entry false or true if whether or not at this row and this column whether this value is null or not. But I can't check for all trues everywhere. So adding sum will count the trues, that is the positive values. If null, it will give me the sum of those values. So we have 0 true, that means 0 null values in this particular data set, which we found and described the info function, info method also. So df.columns will give me the names of the columns, that is 5 columns that we have. So let's go ahead to the visualization. SNS is the Seaborn library, heat map is the function that we're using, and df.correlation, df.corr is the method that gives me the correlation of this data set. Every feature with every feature. A small thing that you can do here, adding annote. Annote means annotation. Annotation in visualization means, do you want numbers, the numeric values of the visualization that has been plotted, the bar plot value, the histogram value, whatever you, if you want the values of that particular visualization, it's called annotations. And adding this annote equals true to the heat map function, this is the parameter, will give you the numbers. All right, so obviously this color bar, this heat map also shows you, but if you want a more holistic, like this will, like you'll have to see which color where it belongs and all that, but adding the annotations will give you the numbers. So obviously this diagonal is the correlation of the column with itself, that is obviously 1. And we see that there is a high correlation between petal width and sepal length, that is 0.82. Even petal length and sepal length also 0.87. Similarly, this very high correlation between petal length and petal width, and petal width and petal length. Obviously, these are the same values only. So when you will work on regression, random forest, and decision trees on your own, you will need to take care of these these columns, very highly correlated columns. But right now, that is outside the scope of this session. But highly correlated features should not be taken together in a machine learning model. Now we will, what we'll do is we will we represent X by our independent features and Y as our dependent feature. So we will take DF and drop the species column and store it in X, that is all the features. And Y, we will take the species column, that is square brackets and the species name, the feature name, into the Y, that is our dependent feature that we have to predict. Now we'll save, we'll split the test. We'll use the train test split, and the X is the train, X is the feature, Y is the predictive variable. Test size is 25%, so the split is 75 and 25. Random state is 0, so that this is actually an ironical parameter that we want to save the randomness. So every time I run the notebook, the random split remains the same, so that if I want to repeat an experiment, I can do that. So the respective splits will be saved in these four variables, that is the X train and X test, Y train and Y test. I'll take a small, I'll just check the chat for a minute. Any questions? Okay, no questions. So now we have our, please explain random equals to 0. Okay, random state is 0. That means I can actually do it 1, 2, 3 also. That means every time in this notebook, in my particular data, for my data, I am splitting randomly X and my features and its respective predictor into train and test data set, so that I can train my model and test how my model is performing on the test data set. I am saving the randomness. That means if I get 2, 4, 6 in train and 1, 3, 5 in test, I want to retain this split every time I run this code. So to retain that random split, I use random state parameter. So if I'm setting it to 1, 2, 3, so every time I do 1, 2, 3, it will give me the same kind of the split. It will retain, like it will learn, it will save my randomness of particular data set. I hope that is clear. Okay. Does it mean that the same row samples are enclosed within a specific? Yes. Yes. Random 0 are different from random 1. Yes. Test size 0.25 means 80, 20, no, 75 and 25. 80, 20 means if my test size is 0, that will give me a 80, 20 split. But I'm keeping it 25. That will give me a 75, 25 split. Just you can check it this way. One, 1, 2. 75% and 25% of 150 is 112 and 38 respectively. So that is our train test shape now. I hope all questions are clear. Yes, no more questions. Okay, coming to decision trees. We will use the decision tree classifier from sklearn. We will create a model function, a model a model variable, and save it in model. We will call this function and save it in model. And then we will use this model to fit on our train data set. So this will fit the model on X train and Y train, that is a train data set. It will learn what features mean which species of flower. This is fitting our model on the train data set. Now we will predict uh, the species on X test. Now we will save the prediction in Y prediction, and we will check the accuracy on Y test and Y prediction. So what we have done is we fit the model on train, both the train. We will take X test and use the model to predict the species. Now we already had the true values of the species, that is in Y test, and we now have the prediction from this model that we fit. Now in accuracy score, I'll use the real values and the predicted values. Always remember here the the order is essential when you're not using the parameter value. Parameter value means this test size equals to, random state equals to. If I remove this, it will understand 0.25, but under different circumstances, it depends on whether this parameter is like the decimal value is unique to this particular parameter. But here, if I'm not using this parameter value, this order is essential. The first is the ground truth, that is the real values, and the next one is the predicted values. Question. I don't understand why we use just model. Okay, so we can, okay, so if I use, no, sorry. Okay, so if you see this, I can use this particular module from the sklearn library, then fit my model and then predict X test. So this is essentially, okay, also the accuracy will change because every time you run the decision tree, it will actually like take features on random and create nodes and subnodes and subtrees differently. So every time you run this model, it will give you different accuracies. So I can do this. This will actually be the same thing, but I'm saving the module, the function in a model variable so that I can use this model and fit it on my data set. I hope, Mia, that's clear. Yes, okay. So we use variables to actually, this is like a programming process. We use variables to ease up our processes, saving variables, saving different functions and methods in different variables. Okay, this is essentially the same thing. So accuracy is 95 right now, 95 again, 95, okay, we have rounded it, that's why, fine. So this is how I'm predicting, and our accuracy is 95%. But remember, this is a dummy data set. Iris is an open source dummy data set. That's why like it has been created to like demonstrate different machine learning algorithms only as a test dummy data set. So that's why 95% accuracy we have achieved without any parameter tuning, without any removing any correlated variables. But this is a very rare case. In actual realistic data sets, you'll have to work hard for this kind of accuracy. So I hope there are no more questions to decision tree modeling. Okay. Now let's visualize a decision tree. For that, we will use the tree module and import this function, that is export graph viz. From 6 we're importing. Okay, these are generic libraries, right? So these are all the display ipython.display import image is for ipython IDEs like Collab, Jupyter Notebooks, etc. And then we're importing py.plus. So we're importing these libraries. Now we're using all the 4 features, and we are using this export graphics function to take our model, the model that we saved here. Out file is a dot underscore data. Okay. String IO is input output in programming. I don't think you'll have to understand this. Our other parameters will make sense. Rounded true, fill true, special characters true, features name, features, that is this list, and class names, the 3 unique class names. So the filled rounded special characters true. Special characters stands for this greater than equal to symbols if we want the diagram to understand and print it correctly. So these are all display attributes and not very essential to our understanding. So you can use it as it is, and like later on you can like explore this particular function and just check what will it do when I change particular parameters. And then I'm saving the graph in this using py.plus.graph from this particular, I think. Yes. Okay. And if yes, I now it has rendered me the decision tree for this particular model. So I think Sneha and Shruthi have explained you how this works. For petal and centimeter less than equal to 0.25, Genie samples 112 it is taken. Genie impurity value is this, and class is iris versicolor, either true or false. So it is just creating subnodes. This is an end node for this particular branch. This branch has various subtrees, and this is how a decision tree actually looks. So this is just a visualization of how
I think Mansi may have some issues on her end, like network issues. So we'll just give it a couple minutes. All right. So until Mansi gets back, I'll just continue with what's remaining. All right. So yeah, I hope my screen is visible. All right. So I think Mansi stopped over here where we were visualizing the data set using GraphWiz. So now I'll go over to random forest. So similarly, what we did in decision trees here was that we basically created an instance of the model. We stored it in a variable known as model and we trained it. And then based on that, we did some testing. So we do the exact same things for random forest. So what do? We first create a random forest classifier. Now, n estimators hundreds means that random forest is comprised of many decision trees. So n estimators is 100 means that there are 100 trees. So you can, like written here, you can select the number of trees by setting the n estimators as 100. So that means that this random forest, particular random forest, is comprised of 100 trees. So we do model fit again. So we make an instance of the model. Okay, I think Mansi is back. Mansi?
Yes, sorry, there was a power cut and my
Yeah, no
router
issues.
UPS is not working.
No issues. You can
Yeah.
carry on. I just continued in the interest of time.
No problem, no problem. Yeah, thank you, Sneha. And I really hope I don't have another power cut, although it's probable, but let's hope for the best. Okay. Random forest, very similar steps. Uh, more, we're just adding one particular parameter. That means we need 100 decision trees to work on this particular problem. And then we are fitting it on the trained data sets. Okay. Then we are predicting like using this model to predict on an X test and checking the accuracy, that is 95%. Importing certain libraries. Okay, here there is a small change. Where here we had only one tree, so we plotted the one tree. But here we have 100 trees, so we need, like for example, the first tree, that is indexing starts from 0 in Python. So this is just the figure plot size, like the figure size for the plot, uh, plt dot figure, and plt is the, okay, matplotlib here. Yes, we are saving all the features in this particular list, and the target is this column, all the species. Okay. And then we're using the tree function from sklearn and the plot function for tree. And from model estimators, we're using the first tree, that is the first estimator. Feature names is these features. Class names is comes from target, the unique values of the target. Filled, impurity, and round are plot features, plot parameters. So you can see that after the session, changing values, Boolean from true to false, what does it give you? Okay, this is the first tree. If we want the second tree, we will use the index 1. One like small question, if I want to plot the last tree of our model, what will this value be? Can you answer in the chat? No, 99, right. -1, okay, yes, -1 also. Correct, correct. -1 also and 99, both are correct. You will see that if you anyway have a issue at any point, you can always check. For example, if you don't want to use -1, you can always check the length of your object, that is 100, and then -1 for the index, and that is your uh, value, like index for the last item of that particular list. So I hope there are no more questions and there are no more. I think there was a question. Okay, Sneha has answered that. Yeah. So for this data set, we had 3 features. I think it has been written here as well. Setosa, versicolor, and virginica. So these are the values for that. The list has the value for that particular, like the frequency of those classes. Yeah. Any question or any feedback, suggestions, please let us know in the chat. I can repeat any code block, any step, any coding practice, any question not particularly pertaining to data trees and decision trees and random forest. Even in the coding part, you didn't understand why we use a particular dot or list or square brackets instead of round brackets. Just let us know. All right, I guess no more questions. Thank you, everyone. Anyway, if you try anything at your own, like at your own leisure after the session, you can be a part of our Slack channel. And on the Slack, we have a channel for this particular study group. And if you try anything and you get stuck anywhere, you can post your question there in the Slack channel as well. And we'll always be there to help you throughout. There is one question. Okay. You're welcome. Sure.
Okay, so that's all from our side for today. Thank you all so much for sticking out till the very end. If you have any questions, please do ask us on the ML study group channel. That's there in both the Python as well as the data science Slack. So the links for the Slack channels have already been posted. So you can join these two channels and ask all your questions there. Hope you enjoyed today's session and see you next week. Thank you so much. I think
Bye, everyone.
we can end the session. Bye, everyone.
Bye, everyone.